So we're happy to have Shuta Nakajima from Meiji University. He's going to tell us about a variational formula for large deviations in first passage percolation.
Okay, thanks for the introduction, and I appreciate this amazing opportunity. Actually, this is the first time to visit India, so I'm very excited, and I have enjoyed a lot of spicy foods. It's spicier than I expected, but it's quite nice. And it's my great pleasure to give a talk at this wonderful conference. Okay, let's start. So I'm going to talk about large deviations in FPP under some estimates of weight distributions. And this talk is based on joint work with Clement Kosko and Florian Schweiger at the Weizmann Institute of Science. Okay, let me first explain my motivation on the research. It doesn't work. Yes. Okay, this is my favorite experiment. This is one of the cheapest experiments that I've ever conducted. And you can see the evolution of the wetting region, and it's a kind of ubiquitous phenomenon in a daily life. But there are a lot of interesting features on this experiment. So I'm going to introduce 3 of them. Okay, the first feature is randomness. Indeed, if we conduct this experiment several times, then the behavior changes from time to time. So, sorry, I'm not good at drawings, but these are the typical example of several experiments, and the dynamics changes from time to time. And actually, this randomness is coming from the state of liquid and also the complexity of materials. And we are interested in how randomness affects this dynamics. Okay, and the second feature is fractal. This means that the boundary of the wetting region has a kind of scaling invariant property. And the third property is universality. So in the next slide, I will explain about this. Okay, KPZ Universality Class. In 1986, 3 physicists, Parizan, introduced a stochastic partial differential equation called the KPZ equation. Okay, it had this kind of form, and I won't go into details, but the point is that by experiment, a lot of interface growing models are confirmed to behave like a solution to the KPZ equation. This is the point. And we call the set of these models, the KPZ Universality Class collectively. Okay, and the KPZ Universality Class can be divided into 2 subgroups. The first one is exactly solvable models. It includes 1-dimensional KPZ equation, TASEP, and 1+1 last passage percolation with exponential distributions and 6 vertex models. And in these models, we can explicitly write down the solution, and we know a lot of properties rigorously. On the other hand, the second model, the second class is unsolvable models, and it includes first passage percolation, direct polymers, last passage percolation with general distributions and vertex deposition, and so on. And it should be noted that most of the models belong to unsolvable models. Okay. Moreover, so far, there are no solvable models for space dimension 2 and higher. And in this situation, my main motivation is develop some techniques which can be applicable to a wide range of models, in particular fast particle percolation. Okay, then let's dive into FPP. Although you are already familiar with the model, I'm going to quickly remind you the setting. So in this talk, we consider DD lattice fast particle percolation. So we consider DD lattice, and let us denote by eta D the set of all edges in DD. And to each edge, we assign a non-negative random variable. So we write down tau E, and we assume that they are identical, independent, distributed. And this notation stands for the path from X to Y. And given the path gamma, we define the passage time of gamma as the sum of weights along the path gamma. Okay, I'm going to explain the situation by drawings. So let's consider D2 lattice. So this picture describes D2 lattice. And to each edge, we assign a non-negative random variable. And in this example, we take a Bernoulli random variable. So the weight takes 0 or 1 with some probability independently. Okay. And a path is a connected line segment, something like this. And in this case, the passage time of gamma is 0, 0, 1, 1. So this passage time is just 2. And we can define the passage time for general paths like this. Okay, from this, we can define the first passage time like this. So infimum over the passage time over paths from X to Y. And we also define wetting region like this. And this is the set of arrivable points by the time t from the origin. Okay, finally, we define optimal paths. An optimal path is a path which attains the passage, first passage time. And we denote OXY, the set of all optimal paths from X to Y. Okay, here is a simulation of wetting region. Is it okay? Okay, no problem. Okay, this is a simulation for the wetting region with the Bernoulli random variable with the parameter 1/4. Okay, in this case. And you can see a pretty outcome of this simulation. Okay, and we are interested in how this evolves randomly. Okay, good. Then I will talk about basic properties of first passage percolation. The first important property is subadditivity of the passage time. It means that the passage time between X and Z is less or equal to the passage time between X and Y plus the passage time between Y and Z. Okay, and the proof is rather easy because the left-hand side is the infimum over paths from X to Z, On the other hand, the right-hand side is the infimum over paths from X to Y, Y to Z. Okay, so there is a restriction that a path has to pass through Y. So from this restriction, we can get this inequality. Okay, and we can regard this property as a triangular inequality. Then we can see that T satisfies the pseudo-metric. And when this probability is 0, then T is exactly a metric almost surely. So from this, we can regard FPP as a random metric space. And in this context, first passage time corresponds to a metric, and the optional paths correspond to geodesics. And that's why these are very important objects in FPP. Okay, good. Next, I will talk about law of large numbers for the first passage time. Before that, I will extend the definition of first passage time as a function on real numbers like this, and this notation is a floor function to each component. Okay, here is the Kingman's famous theorem. So suppose a finite first moment, then for any direction x, the passage time between 0 and nx converges to mu x with this scaling almost surely. And mu x is given by this. And it is a deterministic constant, and it is called time constant. Roughly speaking, mu x stands for the average time from 0 to nx. Okay. And the proof is a direct application of Kingman's subadditive ergodic theorem. So we can safely skip this. But it should be noted that Kingman invented his famous Kingman subadditive ergodic theorem to prove this statement. Okay, so this corresponds to law of large numbers. So next step is to consider CLT and large deviations. And in this talk, we only focus on large deviations. Okay, for simplicity, we only consider E1 direction, and we write Tn mu like this. And large deviations asks the asymptotic behavior of remote tails of sequences of probability distributions. I will refer you to Wikipedia, but so roughly speaking, it considers how the probability that the random variable is far away from the mean decays. And in first passage percolation, in the previous slide, we saw that the n is concentrated around mu n. So we are interested in the probability that the n is far away from mu n. So we consider the following two events. Okay, so given xc, we consider lxc minus and uxc plus. And the first one is called lower tail large deviations, and the latter is called upper tail large deviations. And we are interested in the probability of these events and how they decay. Okay, and the large deviations in FPP, the study of large deviations in FPP was initiated by Kesten. And Kesten first considered lower tail large deviation, and he obtained this result. So suppose the subcritical regime, here PCD stands for the critical probability of percolation model, and also we assume a finite first moment. Then he showed that the lower tail large deviations decays exponentially. And also he showed that this limit exists, and we call this limit the rate function of these large deviations. Yes. Yes. Yes, this one. Yeah, so L epsilon is Tn less than mu minus C times n. And on the other hand, UC plus is Tn larger than mu plus Cn. Okay, the proof is kind of straightforward, so I will show you. First, we rewrite this probability by the products using conditional probability. Okay, it's a standard probability argument. And by FKG inequality, we can get rid of this conditioning. Then we get this inequality, and by Feketti's theorem, by Feketti's subadditive lemma, the limit exists because this probability forms subadditive sequence, and we can apply this lemma. Okay, this is the lower tail large deviations, and the upper tail large deviation is subtler than lower tail large deviation in some sense. Okay, Kesten also considered upper tail large deviation for bounded distributions, and he obtained this. So if tau e is bounded non-degenerate random variables, then for epsilon small enough, then this probability decays e to the minus n to the d. So a kind of volume appears as the scaling. And please note that the scalings are different. And lower tail case, n inverse appears, but the upper tail case, n to the d appears. And later, I will show you why n to the d appears. Okay. And okay, so he obtained this result, but the existence of the rate function had been an open problem for many years, but it was solved by Basu, one of the organizers, and Ganguly and Sly, 2021. Actually, this paper first appeared in 2017, I guess. Anyway. So the statement is the following. So if tau e is bounded and has a continuous density, then this limit exists. So the rate function exists. Okay, this is a very nice result. But a natural question is, what happened when tau e is unbounded? I will show you one result. So in this slide, we suppose that there exists some constants and a parameter r, such that this decay is roughly exponential to the minus constant t to the r. And you can forget these constants, but r is very important. So please remember this parameter r. And then Cranston, Gauthier, and Mountford obtained the following. So when the parameter r is larger than d, so r is here and d is the dimension, then the scaling is the same as bounded case. So n to the d appears. Okay. On the other hand, when r and d are equal to 2, then the scaling is different. We have to put log n here. So from this, one can expect that some transition happened when R is equal to D. And actually, by the same argument, I could prove the following. So when R is less than D, then the scaling is changed by n to the minus R. And then these limits exist and finite. I mean, these limits are finite. Okay. So in summary, okay, let me summarize this. So when R is larger than D, then the scaling factor is n to the minus D. On the other hand, when R is less than D, then the scaling becomes n to the minus R. So they are different. They are different regime. And in the next slide, I will explain why this difference happens. Okay, let's consider two scenarios. The scenario A is that all edges attached to 0 have weights larger than mu plus c times n. Okay, so these red edges have very, very large values. And scenario B is that all edges in the box have weights larger than mu plus c. Okay, so all of the edges inside the box have large values. And note that these scenarios imply large deviation events. I mean, the passage time from 0 to nu1 is very large in both cases. And here, let's compare the probabilities of these scenarios. And when R is larger than D, then the probability of scenario A is e to the minus n to the R because of the tail assumption. On the other hand, the probability of scenario B is e to the minus n to the D. Okay. So the right-hand side is much larger than the left-hand side. So we conclude that scenario B is more likely to happen. And that's why n to the D appears as the scaling. By contrast, when R is less than D, then the probabilities are the same, but the probability of scenario A is much larger than that for scenario B, because R is less than D. So scenario A is more likely to happen, and that's why the scaling is n to the R. Okay. This is an explanation of why the scalings are different. Are you okay so far? Okay, and our result considers the latter case, so when R is less than D case. So here after we suppose this kind of tail assumption, there exist three constants and a parameter R, such that this probability is more or less constant times exponential minus constant times t to the R. And so alpha and R will appear in the rate function, so please keep in mind these constants. Okay, then Kotsko and I proved the following. So suppose R is less than or equal to 1, then for NXC, the scaling is n to the R, and the limit exists, and the rate function is given by this. And it should be noted that the rate function is a power function in this case. Later, I will explain the proof of this result. Okay. Okay, next, we consider the case where R is larger than 1. And before that, I will introduce a P capacity. First, let us consider the M, the box of side length M. And we consider the following class of functions. F is a function on ZD, and F takes 0 at the origin, and F takes the value 1 or larger outside of the box, outside the box. And this is a simple picture, and F takes 0 here, and F takes 1 or larger values outside of the box. Okay, so from this class of functions, we can define the discrete peak capacity like this. And it is the usual capacity except for this power R. So when R is 2, then this is usual capacity, and it has a simple random walk representation. And here, tau 0 and tau m are the heating times of the simple random walk, starting at 0, and in the outside of the box, respectively. Okay, this is the discrete peak capacity, and it will appear in the rate function for the case R is larger than 1. Okay, next we consider the limit of the rate, the peak capacity, and since this function is non-increasing, this limit exists. And moreover, in this situation, R is between 1 and D, then we can show that this peak capacity is positive. This limit is positive. And the second result is about the case where R is between 1 and D. And in this case, the scaling is still n to the R, and the rate function exists, and it is given by this. So the rate function is some constant times C to the R power times P capacity. So in this case, R capacity. Okay. So still it is a power function. Okay, this is the final result. We proved the following. So when R is equal to D, then the scaling is n to the D times this capacity, and the limit exists, and the rate function is given by this. And we and Florian Schwager studied the asymptotic behavior of this P capacity. And the limit of P capacity is the volume of the sphere of this norm with this scaling. From these, we can get complete expression for the rate function when R is equal to D. Okay, these are our main results, and in the rest of the talk, I will explain the proof, the sketch of the proof when R is equal to 1. And for simplicity, we only consider the case where the weight follows an exponential distribution of mean 1, in this case. And in this case, we call the model Eden growth model. So it is a kind of important model, especially. Okay, anyway, the goal is to prove this. And in this assumption, the rate function is just minus 2 dxc. This is our primary goal. First, we consider the lower bound, which is relatively easy. So let E0 be the set of all edges attached to 0. And we consider the following implication. So all of the edges in E0 have values larger than Cn, implies the large deviation event. Okay. I'm going to explain the situation. Okay, so suppose that these red edges have weight larger than Cn, and from law of large numbers, it is expected that the passage time between x and ne1 is roughly larger than mu n. Okay? And combining these situations, we conclude that the passage time between 0 and ne1 is larger than mu plus Cn. Because here it takes Cn and here it takes mu n, then totally it costs mu plus C times n. And that's why one can expect this implication. And it is not that difficult to prove this rigorously. Okay, using this, we can conclude the lower bound easily. Like, from this, we can get this bound, and this one comes from this with high probability. So we can neglect this factor. And since we assume that tau e obeys an exponential distribution, we can explicitly calculate this probability. And then this we can get this bound. Okay, and this implies that the rate function is at least minus 2 dxc. It comes from here. Okay. So the lower bound is kind of simple, but the upper bound is a bit subtle. Before explaining this, I want to introduce one key lemma, which was first proved by Yu Zhang. Large deviations on a slab. And it states that for any epsilon, there exists some constant k and c, such that this large deviation event for the constraint first passage time on a slab is less than e to the minus cn. So this probability decays exponentially. And the constraint first passage time is defined like this. So gamma is constraint in a set A here. Okay, and the slab is like this, and we consider many slabs. So let L be a natural number, and we consider L slabs defined like this. And the picture is this. And note that S0 contains 0 and Ne1, and SL contains 2Le2 and Ne1 plus 2Le2. Okay? And the point is that these slabs are disjoint, so that the constraint first passage time are independent. This is very important. Anyway, we consider many slabs, and these constraint first passage time are independent. And using this, we consider the following, so we can get the following bound. So let epsilon be an arbitrarily positive number. Then the probability that any constraint first passage time is larger than mu plus epsilon times n. So we can realize this probability by products because of independence. And we can get this equality. And by the previous lemma, we can estimate this probability. And finally we can get e to the minus CLN. L is coming from this L. Okay. And if we take L large enough, then this the right-hand side is kind of negligible, super exponential decay. So we can assume the complement of this event. It means that there exists a slab SL such that the constraint first passage time on this slab is less than mu plus epsilon times n. Okay, so we assumed this, and if so, this is the final slide for the proof. So if Pn, the passage time between 0 and ne1 is larger than mu plus Cn, then okay, this is coming from this, and here we apply a triangular inequality, and Tn is bounded by 3 factors: 0 to 2Le2, 2Le2 to Ne1 plus 2Le2, and Ne1 plus 2Le2 to Ne1. Okay, so this is by triangular inequality, and because of this assumption, we can estimate the second factor by mu plus epsilon times n. Okay, so rearranging this, we can get this inequality. And this implication implies this inequality. Okay. Okay, the point is that the event in the right-hand side is a kind of a local event, because this passage time highly depends on the configuration around 0, and the second factor, the second object highly depends on the configuration around Ne1. And this is a local event. And in this local event, we can explicitly calculate the probability as follows. So let's take a 2D disjoint pathes from 0 to 2Le2, and 2D disjoint pathes from Ne1 to Ne1 plus 2Le2. And we can take these pathes from a Kesten lecture note in 1986. And then we note that this passage time is less than or equal to T gamma I. I mean, the passage time of gamma I. The same holds for this second object. So we can bound this probability by this. For any I, the passage time of gamma I plus passage time of gamma I prime is larger than T minus epsilon n. And since the passes are disjoint, we can realize this probability by the product. Okay. And the rest is simple because this passage time is just the sum of independent random variables. So we can apply a usual large deviation argument. And applying this, we can get this bound. And since epsilon is arbitrary, we can let epsilon go to 0, and then we can get the upper bound of the rate function. So this is the whole story, and the main point is that using Slab's argument, we reduce this large deviation event to a local event, and we explicitly compute the local event. So this is the outline of the proof. Okay, let me leave one comment, a case where R is larger than 1. First, let me mention the relationship between this peak capacity and pathwise variation formula. So the right-hand side is the Riemann over the summation of wedge weight, edge weight to the power r, and the conditioning is for any path gamma from 0 to the outside of the box, the passage time of gamma is larger or equal to 1. Okay. The proof is simple, so I skip it, but the argument roughly goes as follows. As in the previous case, we first reduce the large deviation event to a local event. So the passage time between 0 and the outside of the M is larger than Cn. This is Cn. And this event implies that for any path from 0 to the outside of the M, the passage time is larger than Cn. So this is very similar to this condition. Okay. And applying Laplace principle, we can get this approximation. And this conditioning is coming from this event. And the passage is larger than Cn. And this power r is coming from the tail assumption. Okay, and it has a good property. Scaling invariant property. So we can put this Cn in front of the infimum like this. Then it is replaced by 1. And this is just this pathwise formulation. So it is equal to P capacity. Okay, and that's why P capacity appears in the rate function here. Okay, this is a rough argument, and the most difficult part is the first approximation. The first approximation, this one. And to prove this, we have to make a lot of slabs, more slabs than the previous case. But okay, the proof is a bit complicated, but it's still doable, and the same spirit still works in this case. So in summary, so we first reduce the large deviation event to a local event, and we compute the local event by Laplace method. Okay, here I will talk about related models. In the following models, I expect a similar phenomenon that the rate function is given by power functions. For example, for last passage percolation and directed polymers with Weber distributions, I think the same technique works, and one can get this kind of rate function. And also, I'm studying rock models with Hao and Naoki Kubota, and it's almost finished, and we can get power functions as rate functions, and we can get some localization phenomena in this case. And I believe that this phenomenon is kind of universal in the sense that it holds on a wide range of random environment models with heavy-tailed distributions. But okay, I don't know what the exact statement is, but it's my future work anyway. Okay, finally, I list some problems. Suppose tau e obeys exponential distribution, and the first question is about moderate deviations. And here I replaced Cn by entity alpha, and alpha is between 0 and 1. And I think if if alpha is large enough, then the same technique works, and the rate function should be a power function in this case. But I haven't tried it, but it's my feeling. And the second problem is about upper tail large deviations for box-to-box fast passage time. And here we consider the passage time between the box of side length n to the alpha and NE1 plus the box of side length n to the alpha. Okay. And it is well known that if alpha is 1, then this large deviation has scaling n to the d, which is the same as bounded random variable case. So this problem somehow interpolates from exponential distribution to bounded random variables. Okay, this is the final slide, and this is my favorite problem. In our paper, Cosco and I proved the following. So let I plus be the rate function. So here the scaling is n to the d. Okay. And if tau e is unbounded and satisfies this tail condition, and R is larger than D, then we can show this asymptotic behavior as epsilon goes to 0. Okay. Okay, the question is this D the right scaling? So is the right exponent? And okay, the question is this limit is 0 or positive. And my conjecture is this is 0, but it's very complicated, so I couldn't prove it. But okay, I'm very curious about this answer, the answer of this question. Okay, that's all. Thank you for your kind attention.
Are there any questions for Shuta?
Just wondering if your function L plus and L minus, do we have variational representation for them, like we have them in the classical large deviation principle as a Legendre transform?
You mean bounded random variable case?
I mean the case that you want. From the first slide when you mentioned Kesten.
Ah, yes, yes. This one.
Yeah.
I don't know much about the rate function for the lower tail large deviation. I think there is no representation for this case. And I think, for example, convexity is not known and some important properties are not known. So it's quite mysterious region, okay. I guess. And for this case, okay, Basu, Ganguly, and Sly proved this limit the existence of the rate function. And so they do not mention any property about this rate function, but so my colleague Barbara Denbin told me that she could prove that this function is convex. So I think for the upper tail large deviation, it has some representation and it has some convexity or some good properties. Yes.
Okay, thank you.
Yeah, you're welcome.
Any other questions?
Could you say a bit more about that that kappa. I forget what you call it.
P capacity.
Yeah, that one there. Could you describe sort of where this formula comes from and what it represents?
It's okay. The point is the reason why the P capacity appears is from this representation. Okay, so it means that the conditioning is all passes from 0 to dm complement. The passage time is larger or equal to 1. Okay, and this condition is quite similar to this event, right? Because this event implies that any path from 0 to the outside of the box is larger than Cn, as the passage time larger than Cn. So from these similarities, this kappa appears in the rate function.
Can you go back to the
Sure. Yes. When R is equal to 2, then this is the usual capacity. So it's a kind of generalization of the capacity because of this factor R. Okay.
Is there a reason why it's called P capacity?
I don't know. But basically, in nonlinear people use P instead of R, and that's why P capacity. But in this case, we should call R capacity instead. But anyway.
Any other questions? I have a question. So for the upper tail, there was at d equals 2, there was a space transition in the behavior as R sort of crosses d, right?
Yes, right.
Now with your results, do you see similar phenomena in higher dimensions, d bigger than or equal to 3?
So you mean
Cranston,
case?
etc.
Kristen. Yes, I think so. Yeah, their method can be applicable to higher dimensional case, but they do not mention about it. But yeah, I'm pretty sure that their argument still works for higher dimensional case. Yes.
I thought your result covered it. No.
Sorry, what?
Does your result cover R equals D for higher dimensions?
I don't think so.
Okay. If there are no other questions, let's thank Shuta again for a wonderful talk.
Much.